For years, the global electric vehicle industry has revolved around one critical ingredient: lithium. Every major automaker, from Tesla to BYD, from Volkswagen to Hyundai, has spent billions securing lithium supplies, investing in mining operations, and building gigantic battery factories designed around lithium-ion technology. The assumption seemed unshakable. If you wanted to build the future of transportation, you needed lithium. But now, that assumption is beginning to collapse. A completely different battery chemistry is rapidly emerging from China, and it has the potential to rewrite the rules of the EV industry. It's called the sodium-ion battery, and despite using one of the most common elements on Earth instead of one of the most expensive, it is becoming one of the biggest technological threats the automotive world has ever seen. What makes this development so astonishing isn't simply that sodium batteries work. Scientists have experimented with sodium chemistry for decades. The real shock is that China has solved enough of the engineering problems to begin mass-producing these batteries at commercial scale. Suddenly, a technology that many experts believed was years away is rolling off factory production lines, powering electric cars, scooters, trucks, and massive energy storage systems. And if these batteries continue improving at their current pace, they could fundamentally change how affordable electric vehicles become. The biggest weakness of lithium batteries has never been their performance alone, it's their cost and supply chain. Lithium is not particularly rare, but extracting, refining, and processing it requires enormous investments, complex international logistics, and years of mining development. As EV sales exploded worldwide, lithium prices surged dramatically, sending automakers scrambling for long-term supply agreements. Even companies with unlimited budgets struggled to secure enough battery materials to meet growing demand. Sodium changes that equation entirely. Unlike lithium, sodium is everywhere. It exists abundantly in seawater and common salt deposits across the planet. It is thousands of times more abundant than lithium, making concerns about long-term supply far less severe. Countries no longer need to compete aggressively over limited lithium resources when one of the main battery ingredients can be sourced almost anywhere. This dramatically improves energy security while reducing geopolitical dependence on a handful of mining regions. China recognized this opportunity earlier than almost everyone else. Rather than viewing sodium batteries as a replacement decades into the future, Chinese companies began investing heavily in research, pilot production lines, and industrial manufacturing. Their goal wasn't necessarily to outperform the best lithium batteries overnight. Instead, it was to create a battery that could be produced cheaply, safely, and at enormous scale. That strategy is beginning to pay off. Companies like CATL, the world's largest battery manufacturer, have already introduced commercial sodium-ion batteries. Other manufacturers, including Haina Battery, Ferasis Energy, and several Chinese startups, are racing to improve energy density while lowering manufacturing costs even further. Unlike many futuristic battery announcements that remain confined to laboratory experiments, these batteries are entering real products today. One of sodium's greatest strengths is something consumers rarely think about until winter arrives. Cold weather has always been one of the biggest challenges for electric vehicles. As temperatures drop below freezing, lithium-ion batteries lose efficiency, charging slows dramatically, and driving range falls. Owners living in northern climates often experience significant reductions in battery performance during harsh winters. Sodium-ion batteries handle cold temperatures much better. They retain a much larger percentage of their capacity in freezing conditions while maintaining stronger charging performance. This makes them particularly attractive for countries with long, cold winters where lithium batteries struggle the most. For millions of drivers, better winter reliability could become a major selling point. Safety represents another enormous advantage. Battery fires, although statistically uncommon, remain one of the largest public concerns surrounding electric vehicles. Lithium batteries store tremendous amounts of energy, and under certain conditions involving damage, manufacturing defects, or overheating, they can experience thermal runaway, creating extremely difficult fires to extinguish. Sodium chemistry appears inherently more stable. The risk of thermal runaway is significantly reduced, allowing engineers greater flexibility when designing battery packs. A safer battery could lower insurance costs, simplify cooling systems, reduce protective structures, and ultimately make EVs even more affordable. Perhaps the most disruptive aspect, however, comes down to simple economics. Battery packs remain the single most expensive component inside any electric vehicle. Even though battery prices have fallen dramatically over the past decade, they still account for a substantial percentage of an EV's total manufacturing cost. Every dollar saved on battery production directly impacts vehicle pricing. Since sodium is vastly cheaper than lithium, future sodium batteries could reduce battery costs considerably once mass production reaches full scale. Lower raw material costs, combined with simpler supply chains, create the possibility of building affordable electric cars that compete directly with gasoline vehicles without relying on government subsidies. This is exactly why automakers around the world are paying close attention. China's domestic market has become an enormous testing ground for battery innovation. Instead of waiting for perfection, manufacturers are introducing sodium batteries into smaller city cars, compact vehicles, and entry-level EVs where ultimate driving range isn't the primary concern. For urban commuters traveling 30 to 50 miles per day, an ultra-expensive battery offering 500 miles of range often makes little economic sense. A cheaper battery delivering 180 to 250 miles can satisfy the vast majority of daily transportation needs while making EV ownership accessible to millions of additional buyers. This approach mirrors how many successful technologies evolve. Rather than replacing premium products immediately, they first dominate lower-cost market segments before gradually expanding upward as performance improves. Energy density remains the largest challenge facing sodium batteries today. Lithium-ion batteries still store more energy per kilogram, allowing vehicles to travel farther on a single charge while keeping battery packs lighter. Premium electric vehicles, luxury SUVs, and high-performance sports cars continue benefiting from lithium's superior energy density. But that gap is shrinking. Each new generation of sodium batteries brings measurable improvements. Researchers continue discovering better electrode materials, improved electrolytes, and advanced manufacturing techniques that steadily increase performance. The difference between lithium and sodium today is already much smaller than it was only a few years ago. Even if sodium never completely surpasses lithium in energy density, it may not need to. The automotive market isn't built around one perfect battery. Different vehicles require different priorities. A luxury sports sedan focused on maximum range may continue using advanced lithium chemistry. An affordable city hatchback designed around cost efficiency could use sodium instead. Commercial delivery vans operating predictable urban routes might benefit enormously from lower-cost sodium packs. Large-scale energy storage installations connected to renewable power grids could favor sodium because size and weight matter far less than cost and safety. This creates a future where multiple battery chemistries coexist, each serving different purposes. Chinese manufacturers are already exploring hybrid battery packs combining lithium and sodium cells together. Such systems attempt to capture the strengths of both technologies. Lithium cells provide higher energy density for long-distance driving, while sodium cells contribute better cold weather performance, faster charging characteristics, improved safety, and lower costs. Intelligent battery management systems determine which chemistry handles different driving situations. This kind of engineering flexibility demonstrates how rapidly battery technology is evolving. Meanwhile, Western automakers are carefully watching China's progress. Europe and North America invested enormous resources into lithium supply chains, gigafactories, and battery partnerships. The sudden emergence of commercial sodium technology forces manufacturers to reconsider long-term strategies. No company wants to invest billions into one battery chemistry only to discover a cheaper alternative gaining market share much faster than expected. Governments are paying attention as well. Battery independence has become a strategic priority for many nations seeking to reduce reliance on imported energy resources. Since sodium is abundant worldwide, countries can potentially establish domestic battery industries without depending heavily on foreign lithium supplies. The environmental implications are equally significant. Although sodium batteries still require industrial manufacturing, reducing dependence on intensive lithium mining could lessen some environmental pressures associated with expanding EV production. Easier access to raw materials may also reduce transportation emissions linked to long-distance mineral supply chains. Another advantage often overlooked involves recycling and long-term resource availability. As billions of batteries eventually reach the end of their service lives, managing battery waste becomes increasingly important. Since sodium is so abundant, long-term concerns surrounding resource depletion become considerably less severe than with scarcer materials. Still, sodium batteries are not a miracle technology that instantly eliminates every limitation facing electric vehicles. Engineers continue working to improve charging speed, lifespan, energy density, and large-scale manufacturing efficiency. Commercial deployment remains concentrated primarily in China, while global production capacity is still relatively small compared to lithium-ion manufacturing. Yet history repeatedly shows that disruptive technologies rarely begin by beating established competitors in every category. Instead, they succeed because they solve one important problem better than anyone else. For sodium batteries, that problem is affordability. If manufacturers can deliver reliable electric vehicles at dramatically lower prices while maintaining acceptable driving range, consumer priorities may shift. Most buyers don't purchase battery chemistry, they purchase transportation. If one vehicle costs several $1,000s less while satisfying daily driving needs, the underlying chemistry becomes almost invisible. That possibility explains why industry executives are taking sodium batteries seriously despite their current limitations. China's advantage extends beyond simply inventing the technology. The country possesses one of the world's most mature battery manufacturing ecosystems, including raw material processing, component suppliers, cell manufacturing, pack assembly, and vehicle integration. Once a promising technology proves commercially viable, Chinese manufacturers can scale production with astonishing speed. We've already witnessed this pattern with lithium iron phosphate batteries. Once considered inferior to nickel-rich chemistries, LFP batteries gradually became dominant across huge portions of the EV market because they offered compelling combinations of safety, durability, and affordability. Today, millions of electric vehicles rely on LFP technology. Sodium could represent the next chapter in that evolution. Whether it ultimately replaces lithium or simply complements it, one reality is becoming impossible to ignore. The future of electric vehicles will likely involve far more than a single battery chemistry. Competition between lithium, sodium, solid-state batteries, and other emerging technologies will accelerate innovation across the entire industry. Consumers stand to benefit the most. More competition means lower prices, faster technological progress, improved safety, and greater choice. Instead of one battery trying to satisfy every application, manufacturers can optimize different chemistries for different vehicles, creating better products across every market segment. China's sodium-ion battery revolution is still in its early stages, but its momentum is undeniable. What once appeared to be an obscure laboratory experiment is rapidly becoming a commercial reality capable of challenging decades of assumptions about electric vehicles. If development continues at its current pace, historians may one day look back at this moment as the point when the battery industry stopped asking how to improve lithium and started asking whether lithium would remain the king of electric transportation at all.